Hey, Segfault, here. Where are you going? No, I don't mean what location you're trying to get to, but I'm asking about what path you're going to take to reach said location. Every day, as you walk from location to location, you are forming a path. First, let's think about where you start and where you will end. We want to treat this as a graph, which is a collection of edges and vertices. Or in real life, we can think about them as locations and paths that connect them. In graph theory, we can treat these locations as vertices, and every time you stop at a building or an intersection, those become new vertices or points in our graph. As you continue to travel from one location to another, we can think about your path as an edge connecting these vertices. When we have a graph that only contains edges with directions, we call those directed graphs, because there is an explicit direction that each vertex must take to reach another vertex. While we are able to form these paths in our brains, robots need to be programmed to do so. In a sense, we are more efficient than an untrained robot. So, take a few seconds. Give yourselves a big pat on the back. I'll wait. But what if we make those paths more complex? We give you more options. Would you be able to find the shortest path? Highly unlikely, or it would take you at most the time of evaluating all the edges and vertices in the graph if you brute force a solution. In computer science, we base efficiency on a few things, like runtime complexity, how long the program will take to execute given a input, and storage, the space allocated for the program. Since you would need to examine every vertex and edge and test whether you have found the shortest path or not, we have worst case big O of VE time, which is very bad. But what if we were given a more efficient algorithm to find the shortest path? Could we do it? Let's examine a shortest path finding algorithm called Dijkstra's algorithm. Dijkstra's algorithm solves a single source shortest paths problem on a weighted directed graph. For the case in which all edges have weights that are non-negative, I'll elaborate a little bit more on what it means for an edge to have a weight, but let's picture the problem we are trying to solve. We have a collection of vertices and edges, and we want to get from one point to another in the shortest possible way. We then add into the mix weights on the edges. The weights can represent numerous things, like energy being expended on a road or tolls you may incur or want to avoid on the highway. In Dijkstra's algorithm, each weight represents a distance from the vertex, thus we want to minimize said distance when choosing a shortest path. You can think about it as if you wanted to take a road trip and avoid tolls on the highways, while keeping the travel time low. So, how does Dijkstra's algorithm work? The idea is that from a starting point that we have, every vertex that we have not yet visited has a distance of infinity from our starting vertex. Next, look to the neighboring edges and add them to a queue that prioritizes the edge with the lowest weight. We can think of a queue sort of as a lunch line. The first person gets their food and then they leave, and the line continues until we either have 0 people left or we're out of lunch. So, essentially we make what is called a greedy choice, which is a locally optimal choice that will hopefully arrive at a globally optimum. Next, we update the distances of each vertex and then look at the first item in the queue. After we evaluate all the neighbors, we look at the next item in the queue, and the algorithm determines whether any previous path can be replaced with the newly discovered edge. Once the algorithm guarantees that a vertex cannot choose any other path besides the one that it has already chosen, we add that vertex to the known set of vertices that will guarantee a shortest path. And we continue this process until a shortest path is formed on the original target vertex. So, what's the worst possible case? We say that the worst possible case for this algorithm is when it needs to evaluate every vertex and its neighboring edges, and check whether we have the shortest path with the current vertices before it arrives at a solution. The noted runtime of this worst case is big O V plus E times log V. Here's a problem though that we encounter in Dijkstra's algorithm. For example, picture this. You're driving on a highway and there's a car accident somewhere along your path, not necessarily in front of you, but just somewhere along the road. Now, this is obviously going to increase the edge weight if the edge weight is based off of traffic flow, because obviously you have a congested area. Also, let's have a few suppositions. Suppose that the direction you're traveling in is bidirectional, meaning you can go forward and backwards. And let's say that behind you, there's basically no traffic, so it's less congested. And let's also add in one more supposition, is that 3, you cannot get back or you cannot go to your destination from your source if you're traveling in the opposite direction. So, what will Dijkstra's algorithm do? Dijkstra's algorithm encounters a problem here because it will essentially go backwards to the shortest path since it has least weight, which is a big problem because you know that that direction doesn't work and that you need to continue going forward. Now, what significance does Dijkstra's algorithm have? It's actually very useful for planning paths in robotics. For example, a paper published in 2016 by Korea University sought to have mobile robots generate a collision-free path, and within the algorithm contains Dijkstra's algorithm. So, I'm going to sum the algorithm up with a snippet of their abstract along with some paraphrasing and modification for convenience. So their algorithm goes as this. First, we create a surrounding point set by determining the set of points that surround a current obstacle that they're looking at in a loop. And then, after we have collected all of our points, we perform Dijkstra's algorithm to guarantee that there is a feasible path around the obstacle. They also stated that they could use any searching algorithm, but Dijkstra's was used for its simplicity implementation. Finally, there is a path improvement with PIFLP, which looks at the former and latter points, where each point in the path is repositioned according to 2 points on the other side. As a result of this methodology, collision-free paths were efficiently and consistently generated even for maps with narrow geometry and high complexity. And just note that, once again, Dijkstra's algorithm was a part of this to calculate whether we could find a shortest perceivable path around the obstacle. Alternatively, we can use an algorithm called A* search algorithm. It accomplishes the exact same thing as Dijkstra's, where we want to find the shortest path of a single source vertex. And then it uses something called an heuristic function, which is basically a function that approximates the distance between the current node and the target node. The algorithm proceeds like this. We have a source vertex in a graph, and note that each vertex visited stores a distance from the source vertex and a distance from the destination vertex, which is computed using the heuristic function. We want to prioritize the vertices with the lowest sum of source distance and destination distance. If we reach a neighborhood of vertices that are non-optimal, those will be ignored and the algorithm will continue to look towards the next smallest distances. This continues until we have found the shortest path from a single vertex. In fact, we can think about Dijkstra's algorithm as A* search algorithm with a heuristic function of 0 for all the vertices. In practice, if we have a consistent heuristic function which gives us a good approximation, then A* can be much faster than Dijkstra's algorithm. In fact, it at most evaluates all the vertices of a graph due to the heuristic function that is constant time. So we arrive at big O of V. It has been used for many applications, including robotics, although I think my illustration of this algorithm will be subpar to others. I will try my best. Yeah, this is post-editing mod. I did not get a chance to do that. Though, I would suggest watching Computerphile's video for better understanding. So, what did we learn today? We know how to create paths as we continue to travel. The places you visited can be placed into a graph containing vertices and edges that continues to expand as you travel more. The question now becomes, can you find the shortest path that visits all of those locations? I will leave this question as an exercise to the viewer. Thank you for watching. Please don't forget to like, comment, and subscribe. Thank you.